Okay, good morning. Friday lecture. I'm going to talk about lab. This is lab 4. A few announcements in case you've missed it. Lab 3 has been extended until 10 p.m. on a Saturday. I usually push the next lab out on a Thursday. I actually pushed lab 4 out, but it's not in a master of a skeleton. It's just a lab 4 branch, just to avoid confusing anybody who is starting lab 3 late, so that they don't have to worry about what the skeleton master is. I'll merge it into a master after the deadline. But if you're running ahead and you're already done with lab 3 and you want to look at 4, all the code is out. That should be easy. We have a reading week coming up. So next week, there's no lectures, no nothing. And lab 4 is a 2-week lab instead of a 1-week lab. And that's not counting the reading week. So you'll see that we have lab 4 out now. Then there's a reading week. Then there's a week where it's just, there's nothing to submit on Thursday. You just get to work on lab 4. And then this Thursday after that, you do submit. Okay, so use this time to catch up. If you joined the class late and you're behind on the labs, use this time to catch up on labs 1, 2, and 3. Okay, so what is lab 4? So remember our progression. We went from parsing, transformation, parsing. So now it's going to be transformation. Lab 4 is going to be simplification for our F language, for the language of formulas. What is simplification? Well, we want to replace a formula, if possible, by a formula that has the same meaning, that's equivalent, but is simpler. Simpler usually means smaller, has less things in it. You'll see examples, you'll understand immediately what simpler is. Now, we need to understand this problem before we can come up with a solution, and before we can accept any kind of compromise. We need to understand, well, so, is that a difficult problem? What does the theory tells us about what we can do? What should we expect? And this particular problem of simplifying expressions, simplifying formulas, is actually very related to simplifying just Boolean circuits. And it's a problem that's been studied for a long time. We know a lot about it. And the thing that we know about it is it's really, really hard. Essentially, the problem of simplifying is the same as deciding whether two formulas are equivalent. That's known to be NP-complete. NP-complete means that it's a problem that's maybe easy to check once you have a solution, but is extremely hard to solve. And we don't have any algorithms now other than exponential algorithms to do. So what that means is that we probably have to give up an idea that we're going to simplify the formula as much as possible and get the absolute simplest one. We'll need to have some compromise, and we need to base our design decision on that. So what can we do? Well, there's 3 choices that are here. The one that we're going to do is highlighted here on the slide. So one thing is we can pick somebody else's algorithm, something from a book, so the slide mentioned Quinn and Mikulski, and just use that algorithm and not worry and say, okay, does something, somebody else came up with it, we can at least document why we picked it. Another solution is we can use a dedicated tool for solving Boolean circuits. That tool is called a SAT solver. This is something that is fairly recent. About a decade ago, they started to become really powerful. It's a tool that kind of fits in a strange place in theory, because in theory it doesn't work, and in practice it tends to work quite well. But theoretically, I mean, not theoretically, it's in reality, the algorithm itself is still exponential, which means that it's quite unstable. The SAT solver can be applied to very large circuits and work really well, but a small change in the circuit may all of a sudden send it into a tailspin, and it exhibits its exponential execution time and just doesn't work, which makes it really a bad choice for a compiler, because in a compiler we really want a predictable time. So you build your system, you click compile, you want the output to come fairly quickly, and even if it's not quickly, you want it to be predictable. You want to know exactly how long it's going to be, which is the reason why most compiler algorithms are polynomial. SAT solvers are used, and they would be used in this problem where the simplification is really key. So for example, when you synthesize Boolean formulas, when you build circuits, tools that work at that level, they employ a lot of this technology because there, say, before you create the final circuit, you want to minimize it as much as possible. And you don't necessarily care about as much about the time it takes to synthesize as to how small the resulting system is. But so we're not going to use SAT solvers. I mean, they're a good choice for things, but not for compilers. And then the last thing is to use a polynomial approximation. So it's use an algorithm that is polynomial, but it's not going to guarantee the minimal result of the simplification. And the one that we're going to use here is term rewriting, which is essentially taking a collection of more or less ad hoc simplification rules, showing that each rule is correct, and then writing code that applies those rules recursively until no more rules are applicable. We have to show that this leads to an algorithm that it will terminate. We have to show that we make the best choice, that there is no, for example, different applications of the rules that is better than some other one. But other than that, it's just we have a bag of rules and we just apply them. This is what's used by most modern compilers. If you dig into a compiler like LLVM, you're going to find in the middle of it, there's this big rewriting engine, and there's just a big collection of rules. And if you look what happens over years, like if you look at commit history of something like LLVM, you'll see with every release, that particular part of the compiler is extended. And usually what happens is that people look at different pieces of code. Usually, somebody who writes a really tight piece of code and tries to compile it and looks at assembly and says, oh, look, I could have optimized this by hand more than the compiler can, track down what kind of rewrite rule would help, and then the rule is eventually added to the compiler. So every year, sort of just more and more ad hoc rules added, and somehow you have to maintain that, that their application eventually terminates. Okay. So syntax versus semantics, right? So we have, what are we trying to do here? So when we minimize, what are we preserving and what are we giving up? We have syntax, which is how the formula looks like. This is, in our case, we use abstract syntax, meaning we ignore space and comments and things like that. We just look at the abstract syntax tree. That's our syntax. And then we have semantics, which is for Boolean formula, it's truth table, is what the formula means. So when we do a circuit simplification, the step is a semantic step. We want to go from one formula, one AST, to a different AST with exactly the same truth table. That's our goal. And of course, the way we do it is we're going to manipulate syntax, and that's the only thing that we can manipulate. The term rewriting will be a syntactic technique. It will take an AST and syntactically rewrite an AST. On the side, we'll have to prove that the rewrite rules are sound, that is, they preserve the truth tables. But as we implement them, they work directly on the syntax. They just change one AST into another. Okay. So the sort of design games, this is what I've just was explaining about what you'd see in LLVM. Then how far to improve it. We can improve it forever because our technique is polynomial and the problem is NP complete. And because we don't know that P equals NP, in fact, there's a strong belief that they aren't, it means we can keep improving our rewriting rules forever until they, either will remain approximation or become not polynomial. But this is what typically happens in this kind of systems, that you start with some rewrite rules, and then from experience, you see which kind of rewrite rules are useful based on what people tend to use. And also based on what bang you get for this simplifications. The question is, why do we simplify? We often simplify because simpler expressions are faster to evaluate, maybe more less power hungry to evaluate, things like that. And then not every simplification is actually effective at that. And over time, we can figure out which simplifications are more efficient, more effective and keep those. So, right, okay, so that's our game. So let's look at some examples. So what we're going to do first is kind of get the intuition for what those rules are. I'm just going to go through a bunch of examples of expressions and simplified expressions. So let's see. So say we have x or 1. Can you simplify that? You think of it? Yeah. X or 1 is just 1. So that's our first simplification rule. It says if you have an OR and one of the arguments is a 1, then the output is a 1, independent of what the second argument is. And so we might as well simplify this subtree x or 1 into 1. I have a similar simplification rule with a 0. So x or 0. We know that if one of the arguments of an OR is a 0, then the other one is the important one. So this whole thing gets simplified into x. We can now switch to an AND operator, and we have two very similar rules for an AND. Right? The only thing that's different here is that we switch 1 and 0. Right? So we'll say that a 1 is an identity for an AND, meaning that it's like identity for multiplication, that when you apply it, it doesn't change the value. So x times 1 is x, x and 1 is x. In the same way, if we look at here, okay, we'll say that sorry, not here. If we look here, right, or we'll say 0 is an identity for OR. Right? It behaves 0 for OR behaves exactly like 1 for AND. So these two simplification rules are really very similar. They say that 1 is an identity for an AND, and 0 is an absorbing element for an AND. So it absorbs everything into itself. And for OR, it's the other way around. 1 is the absorbing element, and 0 is identity. Let's look at the next one. So we have x or not x. Well, that particular thing, if we draw a truth table for it, it's always going to be 1. So this is 1. And whenever we do x and not x, well, if we draw a truth table for this, this will always be 0. We also have double negation. If you apply negation twice, then the truth table of this is the same as no negation at all. So this is just x. Okay. So this is the kind of rewrite rules we want. So what do we want to do overall is we want to take rules like this, put them somewhere, take an AST that we generate from an F program, and then simplify it using these rules. Meaning that we'll go through an AST, we'll look at some subtree of an AST, we'll see if in this subtree we happen to have something like x and 1, and then we want to simplify it into x. That's the kind of code that we want to write. So now, as we do this, we of course want to apply the rewrite rules more than once. We want to combine them together. And again, this is quite obvious once you look at an example. So say we look here. We have two rules that we can apply. Double negation cancel this. And then x o 0, we said 0 is an identity for OR, so it kills this part. So this whole expression simplifies to x. Look at a bit deeper example. So we have what you see on the slide here. So let's see. 0 is an absorbing element for x. So x and 0 will be 0. 0 is an identity for OR. So this cancels out. And then double negation cancels out. So this should also be x. Okay. Now, one interesting thing is that as you look at these examples, you'll see that when I was explaining the simplification rules, I was applying them either from this way, from outside in, or from this way, from inside out. It's also possible to apply them in all kind of other ways. I mean, it doesn't have to be from one direction or another. So keep this in mind. We'll come back to this. What's important here is that if we combine these rewrite rules, And in order to be sound, we have to identify a subtree, a sub-expression, onto which a rule applies, rewrite the sub-expression, and now we have a new AST, and we can repeat this process again. Look for a new sub-expression to which the rule is applicable and apply. If we do it bottom up, so starting from the inside out, and we're always creating new expressions and always applies rules to the new expressions. So then we know we don't miss anything. If we go top down, then again, we'll also know that we're going to process all expressions. If we're going to go sort of from inside out, back and forth in some arbitrary order, we have to be careful when we write our code to make sure that we don't miss any application that's possible. So let's look at this one. So double negation will cancel out. X and not X, this will be false. So 0. 0 is an absorbing element, so this will be 0. And 0 is an identity for OR, so this will be X. So this whole thing will be X again. Okay, so we see how we can combine the rewrite rules, but we still have a question, which is, okay, so, when should we stop? How far should we go? How do we know that we haven't missed anything? Well, so one way is we can simplify to a point where it's very clear that we cannot simplify anymore. So in these particular cases, we know that we have to stop because we just got an AST of a single variable. Once it's a single variable, we can simplify it much more because that's it. But we don't always get that far. It's not always the case that every input formula is equivalent to a single variable. So what should we do? Well, let me see if you are paying attention. So I'm just going to stop and wait on the chat. Somebody can suggest what should we do. All right, so either there's a very big lag between us, or people are not listening. Okay, so one suggestion that I see in the chat is, all right, just keep applying the rules while it simplifies. Right? And this is, and this is of course the solution we want to do. So we're going to apply the rules while the input is different from the output. The problem here is, of course, that we have to guarantee a priori that the rules are such that we get into a fixed point. Remember that our rules have to be sound. And so we didn't specify yet what kind of rules we want. We just looked at some and said they have to be sound. So let me give you an example of a rule that we don't want to have, but we could. So we can have the following rule. We'll say X goes into X and 1. Now, a rule like this can sneak in if we have lots of rules. We can, mistakenly maybe add a rule like this. When we look at each individual rule, what we really care is whether it's sound, whether in fact it doesn't change our the truth table, the semantic meaning of our expressions. And this one doesn't. That's fine. And then we can also add another rule. X and 1 goes to X, which is the one that we already have. If we happen to have two rules like this, and we say continue and go to a fixed point, that's going to be a big problem, right? Because when we apply this rule, we get an expression to which, once we apply this rule, we get an expression so that the next rule is applicable, and then we get an expression so that the other rule is applicable. So we want to go to a fixed point, and we want to apply those simplifications as many times as they apply, but we have to make sure somehow that we don't have this situation in our rules. So we need to show that this process will terminate. And once we know it terminates, once we know that our rules are good enough, then we can apply it to a fixed point. We're not gonna study how you actually prove that the rules terminate. We're just gonna study that this is important and have an intuition why. Here, for example, it's clear that having these two rules is not a good idea because we always want the rules that take a bigger expression into a smaller one. If you always go from bigger to smaller, then the output is always smaller, smaller, smaller. And since the smallest that the output can be is 1, we're kind of going toward the smaller tree. So there is no way that we can get in a cycle and not get to a fixed point. But if we have rules, some rules that make something smaller and some rules that make something bigger, then we have to be very careful to make sure that we are going to get to a place where we terminate. Right? And if you wonder why would you have rules that go to bigger even when you simplify, so here's one example. So we can imagine that we have an if and only if expression. So that we have this kind of formula. Then one way to simplify it is to turn it into x implies y and y implies x. And the reason to do so is because then the simpler expressions and our other rules will apply. So we're going to go from smaller to bigger, but that still may be fine as a set of all possible rules. It's not the case that we always go from bigger to smaller. Sometimes we do want to go from smaller expressions to bigger because that will help us simplify in other ways. But then we have to be very careful to show that, in fact, the rules will cause us to terminate, that we don't have any cycle. Okay, so I need to get back into presentation mode. Okay. So this is what's going to be true about our particular rule. So we'll need to ensure termination, and we'll check that all of our rules remove at least one element from an abstract syntax tree, and therefore whenever we apply it, we always go down by 1. And so for any formula, we'll simplify it at most n times, where n is the number of tokens. Now the other thing is whether the order of rules matters. Right? So we have a whole bunch of rules for simplification, and we saw even the example that we were doing that we can simplify them inside out, outside in, or in the middle, and it always seems to give us the same result. So if you write your code in one way, and in our test we apply the rules in a different way, somehow we get the same result. That's not by chance. That's by design. Again, it's a property of the rewrite rules that we pick. The property is called confluence that guarantees that the order of application does not matter. Okay? And again, this is not by chance. This is something that we have to show. And if we have a set of rewrite rules which is not confluent, then writing a term rewriter gets a lot more complicated. It's a lot harder to then guarantee that you're going to get, say, deterministic solution, always the same or the smallest. So unless there's something special, you always want your set of rules to be confluent. Now, how do you know that they're confluent? The technical proof itself is not that easy. The intuition is kind of simple. So the intuition is given to you here. It says, if you look at your rules and you see that every time you apply a rule, the left-hand side, whatever they apply to, are all different, then the order shouldn't matter. So if you apply it on one subtree, you don't affect any other subtree. The only time things would make a difference is when you have, say, multiple rules that can apply on the same or overlapping left-hand side. So maybe when you apply one rule, then all of a sudden you disable another rule, and therefore that gets into a problem. Okay, so with all of this, we're ready to start thinking in terms of how we're going to implement the simplifications. This is sort of how our code will look like. So we're going to have a method simplify on an expression. What it's going to do is something like this. For an expression, for each one, for each different kind of an expression, we'll have a simplify once method, which will look at an expression. So it will look at the AST rooted at that particular node and see if any simplification rule is applicable. And it will apply that simplification rule once. So for example, if the E expression happens to be not something else. So when the simplify once here will look, oh, I have a child, I am a node, I have a child that is a node, and so I'm going to return this X as my simplify once. And then once we get the simplified expression, we check whether it actually simpler than the input. So if this is true, then it means that the expression E here and expression simplified and output is the same. So we reach the fixed point, and then we can return. And otherwise, something has happened. This function did simplify something. And so then we keep working. We just update our expression E to be the simplified one, and we go back to the beginning of this loop. Now, this loop condition is true. And so the question is it possible that we get stuck in this loop forever? Is this an infinite loop or not? So again, I'm going to pause and wait for somebody to answer on the chat. It does depend on how simplify once is implemented, but remember, this is not arbitrary code. This is a code that implements the simplification rules that we just talked about. So I'm looking for an answer based on what we talked about. What can you say about this loop? Will not terminate? If you don't know, just say don't know. I just want to know that we're in sync. We can talk about this together. So there's a don't know. So let's see. So we said that this applies one of our simplification rules. And we said that because we want to run to a fixed point, we have to ensure that our simplification rules terminating. And for that, we said we're going to look and require that every time we call simplify, that the result of simplification is an expression that is at least one AST node smaller than the input. So either simplify is not applicable and it's the same expression, or simplify does apply, and then this guy has at least one less node in its AST. That means every time we go through this loop, this expression E, the number of nodes in it, the tree that it represents, gets smaller. And initially, it has some size, whatever number of nodes it is. Every iteration of a loop, it gets at least one smaller. And it cannot go to be below than size 1. It has to be at least one token. And that means that this loop is guaranteed to eventually get to this point. Right. So even so this condition is true, we guaranteed that this condition will eventually become true, because if this condition is never true, and then we keep going through this loop, then this expression gets smaller and smaller and smaller and smaller and smaller. But it cannot get infinitely smaller because it starts with some size, and each time it gets one token less, and at some point it will be token 1, and then it cannot change anymore. Yep, so the question was, this looks like an infinite loop, but is it? Now, the other question here is this is well specified. If you implement simplify and I implement simplify, and we agree on the simplification rules, we just don't agree on how this code is written. Are we going to get the same result? This is where confluence comes into the picture. Because our rewrite system is confluent, which means the order of the way the rules are applied is not important. You always get the same result, no matter how you simplify, which rule you apply first. Because of that, it means that this is well specified. No matter how simplify once is implemented, what rules it looks at, in which order it tries to apply those rules, that doesn't matter. The result will always be the same. It may make this loop work differently. That means the intermediate results will be different, but the final result will always be the same. And if this wasn't clear before, this is what this picture was showing, that if I have this expression and I'm trying to simplify it in two different ways, in this way, I'm first simplifying this part. This way, I'm first simplifying this part. My intermediate expressions are different, but by the time I get to the final simplified result, it doesn't matter whether I went this way or whether I went this way. That's what confluent means. Again, not by choice, not by chance. This was part of our design. When we pick the simplification rules, we check that in fact the rewrite system is confluent, and we check that the rewrite system is terminating. Always gets us smaller expressions, order doesn't matter. And because of it, we can then argue that this kind of simplification loop is good. It will terminate, even so it looks like infinite, and it's well specified. It will always give the same result. So I can ask you to implement it, and I can have my own implementation. And at the end, I can compare and see whether the implementations behave in the same way. And if they aren't, then I know that one of them is buggy. Okay. So now design decision. So how do we gonna do this? Okay. So there's in addition to everything that we've seen, there's a whole bunch of symmetry that we can exploit, and the symmetry will help us in the following way. So it will help us in figuring out how to apply the rules most effectively, and it will also help us with writing less code. So reusing as much code as possible between similar symmetric kind of things. So we're going to look at which way to process operators, right? So we have operators which are on left operand and right operand. Our operations themselves, the AND and OR, are symmetric, so the order of operands doesn't matter, which means we can always get to a smaller expression by sorting the operands, by picking the left and right in such a way that's more convenient for us. The second thing is what we saw already about AND and OR. We saw that 1 for AND is like 0 for OR, and 0 for AND is like 1 for OR. And that means that the rules, the one that said, for example, X and 1 goes to X, this kind of rules, we can share their implementations between an implementation for AND and OR. We just have to be careful to specify, which one applies where, but we can write the same code for both. Right? And then finally, we're going to look at what happens when we have when we want to apply nested simplification rules. Then we can have very deep binary expressions, and then the order in which we apply operations, because this is a heuristic, will not the order in which, but okay, let me just get until we get to an example. But we'll see that. So there's a thing that we can do to avoid dealing with large binary trees, and instead replace them by shallow but bushy trees, n-ary trees. So left-right operators. So the conjunction and disjunctions are commutative. So the order of operation doesn't matter. And so we know that, x and y and x, the order that they come in doesn't matter. So then, as part of our simplification, what we can do is we can always put the operands in some fixed order, so that after we simplify, all of our expressions have, say, the smaller named variable come before the larger named variable. We can do this on alphabetical order of operands, or any sort ordering. And what this is going to do is that it's going to reduce the number of cases in the code that we have to consider. So we'll know, for example, that if we order this properly, for example, a 0, 1 can always come as a first operand or always as a second operand. And so then we only have to check for that. We don't have to handle lots of symmetrical cases. Okay. Now, the second thing is this handling of AND and OR. Right? So again, we can see that the rules are, structurally very similar. So if we look at all of the rules in here, right? If we think in terms of implementing them, they are all going to be exactly the same code. We have an expression, so we have an AST node. We look at its children. We notice that one of the children happens to be special, happens to be an identity, and then we return the other child. Okay? If you think of how to write this code, you would say, check that my right is an identity, and if my right is an identity, then return my left. The only difference between different operations is what is considered to be an identity. Right? What constant is an identity? Is that a 1? Is that a 0? Or something else? And so we can specialize this code that instead of writing the code that looks at the different subtrees and checks which one is identity many times, we write this code once in an abstract superclass. And then in each subclass, we specialize it by defining what is an identity element, or what is an absorbing element for the other simplification rule. And so this is what we're going to do here. So for the AND expression and an OR expression, we're going to implement a special method getIdentityElements, which will return 1 for an AND and a 0 for an OR. And then we're going to have a generic code for that simplification, which will live inside a binary expression. And this generic code will rely on getIdentityElement to do its simplification. Okay. Exactly the same thing with absorbing elements. So an absorbing element is like a 0 for multiplication. So it's the one that it eats the value and makes output be itself. For an OR, it's a 1. And for conjunction, it's a 0. Again, the same thing. We want to avoid duplicating sort of the same symmetric code in both AND and OR expression. Of course, the reason why we want to do this is that that minimizes chances for having bugs and maximizes chances for fixing bugs. If we have the same code or symmetric code or very similar looking code in two different places, and say it's buggy in one place because some test showed it, we fix it in this one place, but the other place is not fixed, and we may forget and not even realize that we made a similar mistake in two places. If we lift this code into a superclass and make it generic and then specialize it in every particular case, then it's higher chance that we'll find a bug, because maybe a test case with AND will expose it, or a test case with OR, and then once we fix it for both at the same time. It does make the code a little bit harder to read, because you have to introduce this new terminology, notion of absorbing, identity. Remember that, absorbing is like 0 for multiplication, which is a little bit harder than having a rewrite rule that looks like this, where you say, yeah, I multiply 0 by x. But the benefit is that there's less code, easier to maintain, and at some point you start remembering what observing means and don't need to look it up all the time. Okay. And so now we come to the n-ary expressions. So we know that the rewrite system is confluent. So when you apply it on an expression, no matter which way we apply the rules, we're going to get the same result. But it doesn't mean that when we apply the same rewrite rules to different expressions, expressions which are syntactically different, but semantically equivalent, that we're going to get the same result. Okay. Now that's an important distinction to understand. So confluence only helps us with expressions which are syntactically the same. We change how the rules are applied. What it doesn't help us is when expressions are syntactically different. Can anybody think why? Can we, do something so that we have rewrite rules so that even for syntactically different expressions, they give a semantically equivalent result? So I'm going to pause and wait for this question to be answered. Syntactically different input, but of course, semantically equivalent give the same result. Because that would be really, really nice. Then we don't have to worry about even small differences in input. Well, this is what syntactically different means here. So here it says like we parse it differently, but really, if we want to be, very clear, we'd say actually the left one we kind of parse assuming there are brackets here, and the right we parse assuming there are brackets here. So these two expressions are semantically equivalent. Once you compute the function, the addition function, it's the same left and right, but syntactically they're different. The brackets are in a different place. And so I'm asking, well, can we have a rewrite rules so that we don't have to worry about this? So that no matter how syntactically different the expressions are, as long as they're semantically the same, once we apply our rules, we're going to get the same semantically, we're going to get exactly the same answer. So we know our rules are confluent. So if we start with an expression, say we start with this one, and you apply the rules in one way, and I apply the rules in another way, we know we're going to get the same result. But what I want is that you start with this expression, I start with this expression. They're semantically equivalent, and we have the same set of rules. You apply your rules, I apply my rules, and I want to guarantee that the output is going to be equivalent. And the question is, can we have this? Is it going to be expensive? Should we expect this? Have we covered anything in this lecture that would help us answer this question? Okay, so again, there are some answers which are sort of which are trying to answer what's on a slide, but not really answering my question. So again, I'm gonna clarify the question again. So what I'm asking is, can we have rewrite rules that take syntactically different but semantically equivalent expressions and produce syntactically equivalent outputs? In this particular case, we're going to show what to do and how we can do it. But before you can appreciate what's going on in here, you have to think about this and think whether you can have a generic solution that doesn't just apply for this kind of trees where you have associative operant, but whether it can be applied just for arbitrary formulas or arbitrary operant. And again, I'm going to wait until somebody says, well, I don't know. And then I know that we're in sync. Okay. Thank you, Ted. It's somebody has to say that they don't know, and that's an important thing to realize that sometimes you don't know the answer, and you have to say this and then try and find ways to get an answer. So this thing, the thing that I have now on the slide, is really hard because if we can have such a thing, then if I have any expression, for example, that is always true, whose truth table is always 1, then I have to simplify it to 1. And if I have any two expressions which are somehow syntactically different, but they represent exactly the same truth table, then my rewrite system will have to rewrite them essentially to a unique representation of that truth table. And we already know that, well, if we can do this, then we can use this algorithm to know, for example, if a formula is always true, or to know whether the formula is always false, because it will rewrite to 1 or it will rewrite to 0. And if we can do this, then we can answer whether formulas are equivalent. And if we can do this, it means that we have an algorithm that solves an NP-complete problem, which means it's not going to be polynomial. It's not going to be, will fit within our framework of polynomial rewrite rules and something that can be done efficiently. So we cannot expect that the syntax doesn't matter. We always expect that syntactically different inputs will cause possibly different outputs. We can fix things a little bit. In particular, as somebody mentioned, well, if things are different, but say you can sort them out, and then once you sort them, they're similar, then we can reduce some of these discrepancies by sorting, but it's always going to be limited. There will always be an example that you could simplify with custom rules for this example, but you cannot simplify using any kind of set of rules that we create. This is what we talked about before when we said it's a design game. We're going to approximate. We're never going to get a perfect solution because perfect solution is theoretically very hard and therefore not appropriate in this particular context. And so we're always going to have imperfect solutions, and we always have to balance this. And whenever we do, improve it somehow, we have to understand what is that we're doing. Are we patching a tiny hole with a very complicated thing, which is maybe not worthwhile, or we're doing something that is a small improvement. It helps. It's not hard to do, and so it's good thing to have, which is what we have in this case. So, syntax will be important, but it doesn't mean that we cannot do anything about it, right? And so the solution here, as somebody said, let's try and put an order on things. So let me get back into my presentation mode. So one solution is, of course, to whenever we don't have any particular brackets, then we just parse it in one particular way. So in our lab 3, the one that you're still doing, so if you haven't done that, we are using this one, the left associate parse. Whenever you have, say, a bunch of operators applied like that without parentheses, we're interpreting it this way. So that's 1. Okay. And then 2, we'll want to, whenever we apply our simplifications, we want to have a canonical representation for those trees. So here, for example, the order here is y, z, x, and so certain simplifications may apply. Whereas here the order is x, y, z, and maybe other simplifications apply. And so we'd like to get to this parse. always, even if an input is not in the right way. Right? So which means we need to sort the operands, but we also don't want to deal with sorting of big subtrees. We can, and some compilers do that you keep all of your operators binary, and then you sort the subtrees. But we don't really want to do this, so we'd rather make sorting easier. So we kind of want to bring all of those guys onto the same level, so that we can sort them using a simple, built-in Java sort routine. Okay. So for this, what we're going to do is we're going to introduce yet another kind of expression. We're going to have n-ary expression. N-ary means that it's not unary, not binary. It has some arbitrary number of children. Doesn't mean that it doesn't have 2 children, right? So n-ary can also be binary, but that the number of children is not known, so they'll be stored in a list or an array as opposed to into individual fields. We're going to have 2 subclasses, an n-ary and an n-ary or. Okay? So we'll get a tree that is going to be wide and shallow, other than deep. And now once we have this, one of the simplifications that we're going to do, and this is a simplification that doesn't make anything smaller, is to sort the operands. Right? So if we have a plus with a different order, then one simplifications can be that we can sort it and go from that one to the other one. As soon as we add a rule like this, we have to think about, will this affect our termination guarantees? And here it won't, because we know that we can only apply a sort once. Right? So if we sort the expression, it's only applicable once. Once it's sorted, if we apply sort again, it doesn't change. So that's what will guarantee that this does not lead, that does not cause our rules to all of a sudden not terminate. All right. All right. So this is, we looked at this code before. So this is what's going to be simplification until a fixed point. So this is inside this the n-ary expression simplify method. And then the simplify once one. So this is this function. I'm doing a good job. So this function looks kind of like this. And so what it's doing, it's first checking that the representation invariant of the expression is correct. So we really want to know that whenever we apply any of our simplifications, we don't break any of the invariants of an expression, that it is a legal expression. We didn't make, for example, some child null or anything like this. We're going to check this before, because we want to know that before we apply our simplification, it's good. And we're going to check this on the result to know that it's good at the result. So this will be good for testing. And then we're going to apply the simplifications in order. And the order that we pick, as we said, is sort of arbitrary. But if you look, certain orders may make more sense than others. And then each operations will simplify. Now this is done using what is known as a builder pattern. And we're going to talk about it in a second, just to understand how this works. But conceptually, what this is doing, it says to simplify once means the following. Apply something that simplifies the children, then merge all of your grandchildren, then see if you can apply the identity element rule, then see if you can apply the absorbing element rule on the result, then see if you can apply the double negation. Then if you have multiple children and they're similar, then remove the duplicate children. Then apply the absorption law, which one, the simple one, looks for whether you have 2 arguments and one is 0. Then apply the subset absorption law. So see if you have multiple elements which subsume others. And then make it into turn it into a singleton expression. So if you have at the end of the day, if you have like an end with a single argument, and then that's going to be a final result. But we write it this way as opposed to, for example, a big nested ifs and else tree, because it's easier to read and less error prone to write. So just to understand how the code is looking, we're just gonna look at, simplify the structure a bit. So it kind of looks like this, right? So we check the representation invariant before, we check the representation invariant after, and then we have a big builder pattern where essentially we have an expression that we start with and we call methods on it. Every method in this pattern takes an expression as an input and produces an expression as an output, and so we can apply them one after another. So what is our representation invariant, right? So this is just something that checks that the expression is well formed. It's any rules that we can put in that will help us in debugging, will help us to detect that something is wrong. And the more rules we can, the more we put. The only requirement is that they have to be easy to check, not something that, say, takes exponential time or something that compares isomorphism or anything like this. Simple checks that represent properties that the class has to satisfy. And if it doesn't, it's definitely a bug. So for example, we check that for any expression that its children list is not null, because an n-ary expression with no children is just not a well-formed expression. That there is no child itself that is null. We require now that children are sorted, right? So we're going to assume that our simplifications sort the children. So now we can check that the children in fact are sorted. So if there's multiple children, then the first is less than the second is less than the third. We're going to look that the children's size is more than 1, because we have an AND n-ary and an OR n-ary, and the smallest AND and OR expressions are binary, so the number of children has to be greater or equal than 2. And of course, this, actually many of those invariants may be violated in the middle. That's why we only check them before the simplification rules and at the end, not at each simplification rule by itself. And in order to guarantee this one, this is where we have the singletonify. Whenever you simplify an expression and it's now of size 1, then you can just replace it by a child as opposed to the expression. So for example, if you had an and let's say, for example, you have x and x, after you remove duplicates, you're going to have an and a single x. And then after you simplify, you just get a single x. Okay, so that's this. And this is just in general sort of a really good thing to follow. That whenever you build a class, you identify what the class invariants are. What kind of instances of this class would be completely illegal, and you put this in a method to check. Often this method will be called rep_ok for representation invariant OK, or maybe is valid or something like this. And then you call this method all over the place in your code in various assertions, so that whenever the representational invariant fails, you know right away. If you don't do this, what usually will happen is that once you have a bug, the bug itself will be in one place, and all it will do, it will affect the class. It will make it slightly buggy. For example, you may have a child of size 1, or maybe the children will not be sorted, or maybe you get null somewhere where you don't want. And that by itself will not cause any failure. And then later, this will interact with some other code, and then eventually you get a test failure. And then finding out this point where the root cause of this failure is extremely difficult. Whereas if you do spend the time to code up what is the representation invariant of each class, and you do go and check it at every point where the class changes, then as soon as you no longer satisfy representation invariant, an assertion fails, you close to the root cause, and it may be quite easy to figure out, what went wrong. Okay, so the rewrite rules that we use, so they are in a lab manual. I hope it is in page 67, but maybe not. Post on campus wire if it's not. The lecture notes and the lab manual are sort of in sync when I compile them, but sometimes they go out. So I haven't checked if it's really page 67 on the latest version, but somewhere inside lab 4 description, you'll see that. It gives you the order in which we suggest to implement them. It tells you where to implement them, gives you the mathematical specifications like the ones that we saw just now. And most of them will be implemented in this n-ary expression, because remember, we have and, or, and not. For not, for unary expression, there isn't much. And or will all convert into n-ary expressions, sort the arguments, and do this. This is where, all of the things that we talked about. So there's a lot of symmetries between different kind of operations, ands and ors. That's all factored out into the superclass n-ary expressions. There's no separate cases for, left, right, because we're gonna parse everything left associative, and there's and order everything, and there's no special cases for and or, because we're gonna do it with this generic property of identity and observing, and right, and there's no funny cases of equivalent but almost isomorphic trees. So this is so what you'll see in there. This is how it's described. So, for example, the first simplification is convert a binary to n-ary. It explains, where do implement them. So this is going to be merge grade children, and what the code should do is kind of go from this expression to this expression. And what it highlights here is that when this operation is applied, the way to implement it is you take your binary expressions and you convert them into n-ary expressions, but of size 2. So this is in simplify once. And then merge grandchildren on an n-ary expressions takes an n-ary expression like this and converts in one like this. Right? So merge grandchildren will apply on this guy, and this guy will say, here's my grandchildren, and I see that they all use the same operator, whether it's an and or an or, and so I can put them all together. Right, and so then we have fold identity element and all the other ones. So okay, so this is what I just mentioned about converting n-ary expressions. So we can do it in 2 steps. Will make life easier. And the first step is to convert from binary to n-ary. So it's the same expression tree, but this is now n-ary expression. And then we convert from n-ary expressions into flat n-ary expressions using merge grandchildren. And yeah, and I think that's it. That's all the slides we have. All right, so that's it for lab 4. So there's a lot of stuff to get through. That's why it's a 2-week lab. It's not very difficult, but it takes a while to get your head around it. And so in the past, when it was a 1-week lab, people really struggled. But with a 2-week period, and we have a reading week as well, usually there is not that many problems. The rewrite rules themselves are fairly simple. The difficult part about this lab is really taking those simple ideas and understanding how to implement them with the data structures. And we're going to force you to use a particular code pattern. And often when one is forced into a particular code pattern, at first it looks very strange and complicated and feels unnatural. But the code pattern that we're forcing you into is the one that's easier to maintain and easier to understand once you get it. And it's a good idea to spend some time and understand it because it's applicable far beyond just this particular problem. There's lots of problems where you have very similar structure, where you have an input, you have some classes, they have to be transformed, you have to have some kind of transformation pipeline, and it will work in this kind of way where you have the builder pattern, where you have iterations, where you have a fixed point, and you have to show that, say, rules don't interact with one another. That's it. If you have questions, ask. And if not, then I'm going to see you not next Monday, but a week from now after the reading week. I don't see anybody typing, so we're done.